Hello there. Today's lecture is about the behavior of fluids, chapter 9. Um, then, first, let's talk about the different states of matter. There are three states of matter: solid, liquid, and gas. Um, Solids have definite shape and definite volume, uh, and then mostly like it's modeled as like having the little atoms attached by a spring, and that means like those atoms like they stay wherever they are, um, but they don't go further. I mean, that means like there is a chance that like depending on the situation they vibrate from their location while they are staying there. On the other hand, liquids, they have definite volume, but not definite shape. uh, Liquids acquire the volume of the container. Okay, so if you take a cup of water, then the shape of that water is the cup. But if you spill it and then put it on another container, and then it's going to acquire uh, same thing like the volume of that. Gases, they have no definite volume and they have no any definite shape. Uh, Molecules are in constant random motion. Molecules exert only weak forces on each other. So if you if you open, like, let's say, a perfume at one corner of the room, uh, then the gaseous particles may travel to different parts of the room, and then at some point they will fill up the room somehow. So that means like mostly they don't have any kind of shape, and at the same time their volume is really mostly contained or pressurized in a container. But when you let them go, uh, 1 liter of gas can occupy like a large volume of uh, a classroom or something. Okay, so one item that we are going to encounter more often throughout the chapter is density, and it's worth knowing it. So, for instance, how do you define density? If density is like the measure of how much mass you have per unit volume, depending on the material, like, for instance, water, the density of water is 1 gram per centimeter cubed. If you convert that to its SI units, um, then that gram centimeter per cube um, equals 1000 kilogram per meter cubed. That's just a simple example. But what does density tell you about an object? So, for instance, if you take a bucket of, let's say, water, and if you take like a bucket of, let's say, as an example, maybe a lighter material, let's say alcohol, maybe. Even though the volumes are the same, but if you try to lift it up, then the water may be slightly higher, heavier than the alcohol. The reason is because the molecules in water are more compact when they are compared with that of the molecules in alcohol. Likewise, if you consider like metallic object, let's say water, a bucket of water, and a bucket of, let's say, mercury, which is a liquid metal. If you compare those, mercury has about like 13.6 gram per centimeter cubed density. That means that bucket of mercury can be 13.6 times heavier than water itself. Okay, so in general, its density is calculated if you know the mass, the amount of mass that you have, and per unit volume. That's what it means. So if you try to really use your imagination, and what does that mean? Like, for instance, 1 meter cubed means like if you make a container, let's say a container made of like 1 meter by 1 meter by 1 meter, Okay, so if you have a container or a water tank, let's say, if you have a container like that, which is 1 meter on the side, so the volume of this container is 1 meter cubed, right? So if you fill up this container or this water tanker with water, how much water are you going to be able to fill in? Then that is just literally 1000 kilograms. Okay, that's what this literally tells you. Like in one per means like one, in 1 meter cubed volume you get 1000 kilograms kilograms of water. Okay, so and what is the relationship between density and temperature? Like when you heat up some material, what happens? They expand, right? That means its volume increases. If its volume increases according to the previous equation here, then most likely its density decreases. Okay, maybe to a certain level water is an exception. Why? Normally when you cool down stuff, the opposite effect happens. That means the molecules shrink, and then somehow, like, they occupy lower space, smaller space. Because of that, what happens is, like most materials, when temperature decreases or when you make them colder, their density increases because their volume decreases. But for water, that doesn't happen to a certain level. Why? You can demo it like in ice. Ice floats in water. Ice is solid. The solid, like solid ice means solid. Ice means like solid water, right? When it shrinks, I mean, supposedly it was supposed to shrink when you reduce the temperature, right? But for water, that doesn't happen. Okay. Then the next item is specific gravity. Specific gravity means the comparison between the density of any object relative to the density of water. The density of water, as I mentioned it earlier, okay, the density of water, like at 4 degrees Celsius, is 1000 kilograms per meter cubed. So specific gravity is just a relative. So the density of anything, like an SI unit, any material, right, kilo per meter cubed, it can be anything, gold, water, I mean anything. Divide that by the density of water. The density of water is 1000 kilogram per meter cubed, right? So the units cancel out, then specific gravity becomes a unitless ratio. Now, the next item that we're interested in this material is pressure. So the concept of pressure, it's a little something that you usually note, but probably you might not have seen it like from physics perspective. So for instance, like if you take like two people walking in the sand, right? So just simple, this is sand. Someone is like walking, let's say, barefoot, okay, but on the other hand, somebody else is walking over here on high heels, right, on a sand. Okay, so what will you notice? The person who is walking on high heels, like assuming that like both are the same mass, okay, if both have the same mass, you will note that like the person who's wearing high heels makes holes or dimples on the sand. That means it literally punctures it. Why is it happening? I mean, if both have the same weight, so the reason is somehow it's connected in terms of pressure. because the weight of this person is uniformly distributed on a larger surface area because his bare foot is relatively flat, whereas the weight of this person is being transferred to the ground in a smaller area. In other words, this person A applies higher pressure on the floor than person B, and by definition, like you can see that like P is equivalent to force over area. That's how you define pressure. You can take that like same kind of concept, right? So for instance, if you push your the back of your hand with your finger, right? Push it hard, you might not feel anything. But on the other hand, if you try to do same thing like with a pin, then definitely this can easily puncture your skin, and then you'll feel the pain. The reason, again, the same amount of force, even though you apply the same amount of force on both scenarios, the force that you are sending through the pin is being transferred in a very smaller area. Okay, so for that reason, then the pressure here is higher compared to the pressure in here. So this pressure concept has like a very wide kind of concept. It's applicable in at so many levels in science and in engineering and so on and so forth. Okay, so something that we also would like to know about pressure, especially pressure in a liquid. Okay, that means the equation we just saw here, that pressure normally, this is like a general formula. It's a general equation. It's applicable anywhere. And then the SI unit of pressure will be the SI unit of force, right, divided by the SI unit of area. The SI unit of pressure again will be the SI unit of force is Newton. The SI unit of area is meter square. So Newton per meter square. And this Newton per meter square has special name known as Pascal. This PA, or if it's in writing, you can write it like Pascal. When you write it in full name like Pascal, use a small letter P. Okay. Then how does pressure vary in a liquid? Okay. So in a liquid, so if you consider like pressure, like if you are swimming at this level 1, so let's say this is a lake, and then if you swim at level 2, if level 2 is at a lower depth relative to the surface, so if this is the surface, the symbol of the surface, then what you would feel is like the person who's swimming at a higher depth will experience more pressure than the person over there. Okay, so something for you to think about it is like pressure varies in a liquid, varies with depth, nothing else. It doesn't matter. Like for instance, if you take a frog and you put it put it in a barrel of water, and the frog is swimming at a depth of, let's say, 1 meter. If you consider a lake, assuming that there is no any hydrodynamics, that means not the water isn't really moving or anything, and then here's your frog, and then there's another frog in a lake. This is just a simple container or a bucket of water, okay, or a barrel. Right, this is like a lake. And then if you have a frog that is swimming at a depth of 1 meter, okay, then which one do you think will experience a higher pressure. So according to this, we're limiting ourselves like just to the concept. We're not going to do any of the proofing, but it can be proved. Only pressure varies with height. What does it mean is like as far as the density of the water that you have in the bucket in the lake are the same, then the amount of pressure experienced by this frog will be the same. Okay, it doesn't matter like whether you are swimming in a swimming pool or if you are swimming in a freshwater lake. As far as you are swimming at the same depth, you will be experiencing the same pressure. Okay, so that means the container doesn't really matter that much. So then that means what would be the formula for the pressure that you will experience with height? Pressure is going to be density times gravity times height, depending on the density of the fluid, depending on where you are swimming from the surface, then that is how much pressure you are going to experience. So this is normally, we call this like as a gauge pressure. Okay, but there is something that we never deny, that is called atmospheric pressure. There's atmospheric pressure. Atmospheric pressure means the pressure of the air that's surrounding us. Okay, you can consider the pressure like this. Like for instance, this is the earth, right? And imagine that like you are on top of the earth, right? But the thing is now, because of air, like as we were saying, like any fluid, there is atmosphere that is surrounding the earth. Okay, and it's an exaggeration version of it. Okay, this is not to scale, of course. Then because of the green area is like the atmosphere, that means air, literally. So because of that air, right, that means literally you are swimming in air in your day-to-day life. That means like you are carrying this much amount of air on top of you wherever you are going. Okay, because of that amount, because of that depth, about like 12 kilometers or something like that, then you are carrying that much amount of air all over. You are walking. Okay, that's about sea level. Then because of that air on top of your head, since you are swimming, literally right now you are swimming in air, because of that, then you are going to feel this much amount of pressure, which is about like 100,000 pascals. It's a lot of pressure that you feel on a day, but our body is designed and acclimatized to that scenario, so therefore that's how we live. Then probably before we go ahead and do something about like Pascal's principle, it's worth like looking at an example. Okay, so probably it's going to be a simple example that we will look at. So in your textbook there's E1. Okay, so E1, normally it's a very simple kind of question. It asks you, a force of 16 Newton pushes down on the movable piston of a closed cylinder containing a gas. The piston's area is 0.4 meters square. What pressure does this produce in the gas? So you can just simply apply the definition, the one we just said, then to solve it. Okay, so what you can do is apply pressure. Pressure is equivalent to, so this is simply, what are your given parameters? So the given parameters are the following. There is force, then the amount of force that is acting on the cylinder is given as 60 Newton, and cross-sectional area is 0.44 Newton. Then you are asked to determine how much is the pressure. So the solution for this problem is straightforward. Just simply apply the equation pressure equals force over area. Then of course it's going to be 60 Newton over 0.4 meter squared. This is meter squared. Then if you simplify this, what you are going to get is 150 Newton per meter squared. Has a special name, we call it Pascal. Okay. Awesome. So the definition is pretty straightforward. Now the next item is Pascal's principle. So according to Pascal, his name is Blaise Pascal. He's a French scientist. He was. Then what he said is, like, in an enclosed fluid or in an enclosure, pressure from one location to another location transfers without being diminished, or it says like undiminished pressure travels within that enclosed fluid without being diminished. Okay, so a good example for this one is like, for instance, you take a forklift or a hydraulic brake. So if you consider that, like, as you can see in this diagram, what you have is like a car lift. Most of the time you may have seen this like in a garage. So this is a detailed part of it. But if you go to a garage and then if you see those people like lifting a car, what do? They just barely apply a very small amount of force on the piston, and then all of a sudden you will see the car being lifted, right? So in general, the principle is as simple as the following. The amount of pressure that you apply over this cross section on this side of the system will be transferred on this side with the same amount. Okay, that means pressure at one location is equal to pressure at two. Then the pressure at one being transferred into the system equals the pressure at two. Okay, so it means, like, you have pressure, and you are applying pressure on one side of the car lift, then that pressure will be transferred literally throughout the system, being undiminished. Okay, so that means, like, without losing any of it. Okay, of course, like, there shouldn't be a leak or anything. Even car brakes nowadays follow this hydraulic system. By just simply pressing the brake pedal, you can stop a moving car. That's as big as, like, a tremendous amount of force. But in general, that's based on the principle of Pascal. So how do you find pressure on this side? Then pressure on this side can be calculated as force 1 over cross-sectional area 1. And on the other side, it will be force 2 over cross-sectional area 2. Why? Because the pressures are the same. Of course, the forces and the areas will definitely be different. Okay, so having said that, probably it's worth solving a few examples. Let's go to the end of the textbook, and let's try to solve E5, something really perfectly similar to what you are seeing here. So I'm going to read it for you. The problem states, like, in a hydraulic system, let's switch to the whiteboard. Then E5. It says in a hydraulic system, a force 540 Newton is exerted on a piston with an area of 0.002 meters squared. The load-bearing piston in the system has an area of 0.3 meters squared. What is the pressure in the hydraulic fluid? What is the magnitude of the force exerted on the load-bearing side? So I'll try to sketch the diagram. And of course, before that, let me list my given parameters. Given force on one side, 540 Newton. Okay. Then a corresponding area on the piston side, given as 0.002 meters squared. And on the other side, on the load-bearing side, you have A2, given as 0.3 meters squared. So if you try to sketch it, so you can sketch it the way I just showed you in the slides. So let's assume that like you have a scenario like this. Okay, then this is where the load-bearing side is. So let's assume that you're trying to lift a car, sitting on the load-bearing side, by applying force on the piston side. Then there is a cross-sectional area for A1, there is a cross-sectional area for A2, and you're applying force F1. That means you're just pumping it up and down on that cross-section to lift the car. So the first question states, A, how much pressure is in the system? The pressure is not going to be diminished according to Pascal's principle. Okay, so pressure is the same everywhere. Okay, so throughout the fluid it's the same. So therefore pressure in the fluid is the same as pressure that you're applying on piston 1. If you can find the pressure on piston 1, then that's it. But the pressure on piston 1 can be easily found using the formula that we know. Pressure equals force over area. P1, 1 means like its name. You can have one pressure, you can have two pressures, you can have, like, it's like saying people 1, people 2, people 3, and so on and so forth. Okay, but we have specific names. So the amount of force acting on the piston side is 500 Newton, 540 Newton, and the area acting on that same side is 0.02 meters squared. So if you simplify this, what you are going to get is 270,000 pascals. All right. Now, the second part of the question states that B, what is the magnitude of the force exerted on the load-bearing piston of the hydraulic fluid? So on the load-bearing side, how much force you are experiencing? Okay. So to solve that, what you are going to do is just simply apply the concept of Pascal's principle. So B, you are asked what is the force on the other end. So on this side, that means like what can be like the maximum weight of the car that you can lift on this side. Okay, so that can simply be found by the concept that pressure on cross-section one side is the same as pressure on the other side. That means pressure on the piston equals pressure on the lift side or the load bearing side. You already know the pressure on one side, the one you just calculated, this guy. Therefore, you can say 270,000 pascals is equivalent to P2. But by definition, P2 is F2 over A2, right? So 270,000 Pascal equals force 2 over area 2. So to isolate F2, what will you do? You multiply both sides by area 2. Side 2 by area 2. Then A2 cancels out with this. Then you will have F2. So therefore, from here, you can find F2 equals A2 times 270,000. But A2 is 0.3 multiplied by 270,000. Pascal, of course, this is meter squared, the unit. This is Pascal. Pascal means Newton. Yeah, Pascal means Newton over meter squared, right? So that meter square cancels out. Of course, instead of Pascal, you're using that. So multiply that, then you can find the value of F2. And F2 is about 81,000 Newton. Okay. That's it. So then that's how you can normally find how this thing works. Okay. All right, so let's get back to the lecture part. So now I hope you understood what Pascal's principle and its intentions are. So the next item is probably how do you measure pressure? So using manometers. Most of the time they follow the concept of manometers is it's like you have some kind of a liquid, most of the time mercury, in a U-shaped test tube, and then you connect this end of the pipe where you see this P, right? And then you connect it with this manometer, and then automatically the fluid on the other side will rise. It rises because of the pressure that you have in the pipe, right? Then if you apply, the concept that we said, pressure varies with depth, right? So if you have this much depth, then you can find pressure using density times gravity times height. That's pressure in a fluid. But how do you measure atmospheric pressure? An Italian scientist came up with an idea to measure atmospheric pressure. Atmospheric pressure is measured using barometers. Barometer is just nothing else. It's just simply a combination of test tube and a ball. So according to Torricelli, what he did is he had put in ball of mercury in a container, and then he filled up a test tube with mercury again. And then what did he do? He bring this thing and then flipped it in here. Then as soon as he flipped it, what would happen is the liquid in the pipe will rise, and then there won't be any kind of air left. Okay, that's what the idea of flipping it inside. Then this height, or this rise in height, is the same as pressure, because according to the definition that we saw, pressure only depends with height. That means if points are at the same level, the pressure due to at the atmosphere at this level, and the pressure that happening here because of the height of the mercury that you have here are the same, because it's only the depth where you are dictates how much pressure you experience. Okay, if you take a point here, this point, and this point, all those 3 points will experience the same amount of pressure from the fluid, because they all are pretty much at the same height. You may say this is, but this is at this height, this is at this height, but this one is at this height. You may say like that, but because those two, they experience additional pressure from the atmosphere. But anyway, he used that technique to measure atmospheric pressure. Then of course there is a blood pressure that we measure. Every time when you go to a doctor's office, they use a tool, they call it sphygmomanometer, that measures blood pressure. Okay, mostly they take it to your right hand, mostly, and then they put it on over here on your arm, then they measure your blood pressure. So one of the main reasons they put it like at arm level, because this is level to your heart. Your heart is here and it's the same level. That means getting pressure here means getting pressure there. In an enclosed system, at the same height, you experience the same pressure. If they try to measure your pressure over here, which is lower than your heart, then it's going to be a different story. So that's why, like, the doctors prefer to measure your heart, your blood on your arm, specifically around this area. Okay. So pressure values, atmospheric pressure, as mentioned earlier, atmospheric pressure is approximately 100,000 Pascal, but that can also be considered as 76 centimeters of mercury. Okay, so we can go ahead and then see Archimedes Principle. Okay, so what is Archimedes Principle? What does it? What did he basically study about pressure and fluids? So the following. He was a physicist, he was an engineer, he was an extraordinary mathematician. So according to Archimedes, what he said is like any object that is completely or partially submerged in a fluid experiences a buoyant force, experiences an upwardly force that is called buoyant force. That's why, like, you try to swim in a liquid, you feel lighter than yourself, because that happens because the liquid pushes you up, and that force is because of buoyant. That's what we call buoyant force. You will be buoyed up. Okay. All right. So then, according to him, what he said is like the amount of buoyant force that you experience, or any object that experiences, or you see boats floating, they literally use that principle. What it says is like buoyant force is equal to whatever you displace. So that means if you see like a boat floating, it means the amount of water that boat is displacing, right? The amount of water that boat is displacing. Okay, that means in terms of weight. If you can find the weight of the fluid that is displaced, right? That weight is the same as the amount of buoyant force. Okay, it involves like an intricate design, mathematical calculations, and so on and so forth, to figure out the right shape, the right amount, and so on and so forth. But in general, like what keeps like a boat floating is the buoyant force, and that buoyant force is the same as like the weight of the displaced fluid. Okay, so you may say, like, how do we end up with this equation from this? So you know that weight, we defined weight is mass times gravity, right? And around the beginning of this material, we defined density. Density of any object is the amount of mass per unit volume. To find mass, if you isolate mass, you need to divide both sides by volume. Then therefore you will find mass is equal to density times volume. Okay. Then you take that and substitute it in place of m. Then you will get weight is equal to density times volume times gravity. So the amount of buoyant force that any object experiences is the same as like how much you are going to displace. Okay, so buoyant force is always exerted by the fluid. Okay, yeah, whether the object sinks, floats, partially floats, whatever the case is, then it experiences buoyant force. Okay, so probably it's worth trying to go ahead and solve a problem. So in your textbook, E10 states the following. I'm going to write my given parameters. So E10 states a 0.52 kilogram block of wood. So the mass of the wood, or the block, you can call it, is given as 0.52. It's floating in water. What is the magnitude of the buoyant force acting on the block? So you have been told floating. Then how much is F buoyant? I'm asking you this question, a very simple question, but at the same time, everyone who takes the a general physics class, I want you to understand what is happening here. So the problem literally states the following. So you have, say, you have a container, and then you have a block in there, say the block, and then the block is just floating in water. It's floating. It's not falling. It's not rising up, but it's falling. So if you try to see all the forces acting on this block, right, then first, something that you will notice is its weight. Okay, the weight of the block. And the other force acting on this guy is, of course, the buoyant force, because of the water. So, for a floating object, the total weight of the object is totally or completely supported by the buoyant force. Okay, if the object floats, like this is the thing that I want you to keep always in mind. For a floating object, as far as the object is floating, okay, for a floating object, the weight, you can put it as the total weight the object is completely supported by the buoyant force. That means this object is floating because its weight means the block. I use the term block, right? FB is for buoyant. Its weight is completely supported by the buoyant. The two are cancelling each other. One is acting up, the other one is acting down, and the two are cancelling each other. That's why the block is not sinking or it's not rising. If the weight was larger than the block, the weight of the block, right? I mean, if the weight was larger than the buoyant force, then slowly but surely the wooden block will fall down, okay? So therefore, the buoyant force will simply be equal to the weight of the block. And we know that how to find the weight of the block. The mass of the block multiplied by gravity. So therefore, F buoyant will be equal to, the mass of the block is given, we already wrote it as 0.52 kilograms. And gravity, you may use 10 if you want to, but just to be a little more precise, I'm going to use 0.98. So therefore, the amount of buoyant force that is acting on the block is about 5.1 Newton. So every time that you are seeing floating object, any floating object, keep in mind that the object is floating because its weight is completely supported by the buoyant force. Okay? Probably it's worth adding more questions. This one is a simpler version of Archimedes Principle, but I expect everyone just to know and remember this in the future. E12, it states a certain boat. So given there's a boat now, boat is involved. A certain boat displaces, that means the volume of the displaced fluid equals 8.3 meter cubed. The density of water, or fluid, I'm using the term fluid, what is fluid, by the way? Anything that flows. Gases are fluid, liquids are fluids, okay? Is of course 1000 kilogram per meter cubed. That's also given because it's water, then it's fresh water. What is the mass of the water displaced by the boat, and what is the buoyant force acting on the boat? Okay. So now for part A, you are asked to determine what is the mass of the water displaced. So the mass of displaced equals what? So mass is density times volume. Okay, the density of the fluid, because it's a fluid that's being displaced, multiplied by how much volume is displaced. Okay, so the density of the fluid is 1000, and the volume of displaced is 8.3. Okay, then this meter cube by that meter cube cancels out, and therefore the mass of displaced is equal to mass displaced equals 8300 kilogram. Okay, then you go to part B. And part B asks like, what is the buoyant force acting on the boat? F buoyant. Buoyant force, according to Archimedes Principle, is the same as the weight of the displaced fluid, right? He already said it. Since we already have the mass, we don't have to start all over again, density of fluid, volume of fluid, gravity. Instead, just simply, buoyant force will be weight displaced, means, right, from the weight definition that we covered when we were talking about like Newton's laws, right? So the mass of displaced multiplied by gravity. You can take 10, you can take 9.8. It's up to you. That's for your G. And the mass, we already calculated the mass, 8,300 kilogram. Multiply that by 9.8 meters per second square. Then if you substitute those values, you're going to get is about 81,340 Newton. Okay, so always have your calculator in hand. Okay, then that's how you find the value. Okay, so and that's what the buoyant force is basically. Then buoyant force is exerted by the fluid. We already said it. So whether the object is sinking or not sinking, always like keep that in mind that it experiences a buoyant force. Now, the last item most likely that we would like to cover in this material is the equation of continuity. Okay. Equation of continuity means like if you let water pass through a pipe, and if the pipe has a variable diameter, that means if it's like, at some point, if it is constricted, at some point it may have a larger diameter and so on and so forth. But the amount, the weight of water passes at the cross section, okay, of 1, as you can see it in the slide, and at cross section 2 will be the same. Okay, will be the same. So if you try to go through that means like, it's like you let water to pass through this and then to go through this. Then water is not really compressible. So the amount of water, like let's say 1 liter of water, you see this shaded region? This 1 liter of water that is crossing in 1 second at cross section 1 is the same amount. That means 1 liter of water will cross up this cross section in 1 second. The only difference that you see here is, what do you have? In a smaller or in a constricted area, right, the water occupies a larger or seemingly larger area. But in other words, what it means is like, if the area is constricted, to let that much amount of water to pass through it, what has to be is, you need to have a higher velocity. So the velocity of the water at a constricted location has to be higher. Velocity is higher here because the velocity has to compensate the constriction in area. On the other hand, if the pipe is larger in diameter or in cross-sectional area, therefore the velocity can be slower because you already have a larger quantity. But in any way, the amount of water that's crossing in 1 second, if 1 liter crosses here, 1 liter will cross there. Okay, that's why, like, hoses, like for gardening or for firefighters, you see that like the water is coming in a larger area, but eventually like the hose is constricted because whatever water is coming, right, when it's leaving, because this area is very small, whatever water coming through this, and a larger, water is coming, like 1 liter of, let's say 1 gallon per second or something. That's a huge amount. And when it leaves this one, it has to come out at an extremely high velocity. Okay, because over here the water can't relax because there's a larger space and its speed can be slower. But here it has to rush out because there are so many of the waters trying to pass through in a smaller cross-sectional area. So this equation of continuity literally says that the flow continuity says that area 1, that means the cross-sectional area that you have here, multiplied by the velocity that you have here, equals the area over here multiplied by the velocity that you have here. Okay, so that's what like the law of continuity states. It's a very simple kind of continuity equation. Probably it may worth like to try to find or do an example. Okay. So let's try to find an example. So in your textbook E14, you can do E14, but otherwise, like we can also do a better kind of question. So the concept of continuity, this is what it says. Like, actually there is an example in your textbook, and let's do it. So this example, use my whiteboard. 9.4. It says like, look ahead at the circular pipe shown in a figure 9.24. Assume it has a radius of 6 centimeters in the wide part and 4.5 centimeters in the narrow part. If the fluid is initially flowing at a rate of 2 meters per second in the wide part, what is the velocity in the narrow part? So the diagram somehow looks like there's a pipe, there is water flowing through it, and then there's a constricted area. So it says you can call this diameter 1. The diameter here is 6 centimeters. The diameter here is made it a little smaller. The diameter here is, you can call it diameter 2, 4.5 centimeters. If the initial velocity, that means V here is 2 meters per second. V2 here is what? Something that you need to keep in mind is look at the problem and try to judge your answers first, like, So I already mentioned that, like, if the area is larger, the speed is slower relatively. In other words, the cross-sectional area is what? Smaller. Then you would expect a higher value. So that means your answer definitely has to be more than 2 meters per second. Otherwise, it's not right. Then you will have to look at it. So this is a continuity equation. Then you will apply the equation of continuity, which is A1 V1 equals A2 V2. Okay. The amount of water flowing in cross-sectional one has to be the same as the water that is crossing it. So how do you find area? This is a pipe. The area, the cross-sectional area is, pi r squared, if you want to follow the simple one. Or you can use the diameter at the way it is. Both are the same, depending on what is given. Okay, by d squared over 4. So therefore you can find the areas. So you can find area 1. So area 1 will be pi times the diameter is 6 centimeters squared over 4. You can keep it in centimeters squared, it's fine. Then the area is 113.1 centimeters squared, because the area will cancel each other anyway. Then area 2 will be pi times 4.5 squared over 4. Then area 2 is calculated as 63.6 centimeters squared. Then now you substitute those values into the continuity equation. The continuity equation again, A1 V1 equals A2 V2. A1 is 113.1 times V1 is 2. A2 is 63.6 times V2. To isolate V2, what do? You divide both sides by 63.6. Okay. Then this will lead to a solution for V2, and V2 is approximately 3.56 meter per second. Okay. But anyway, just remember, if the area is constricted, that means if you're letting the water to pass through in a narrower path, then you should expect a higher speed. Okay. So I think this is the end of the material. You try to solve as many similar problems as you can. Until the next time, then bye.